Hi, I'm Sabir Liaquat. I'm an engineer at Teledyne Princeton Instruments, and welcome to this seminar, which is the third part of this series with Python automation, and we'll get into some real-time frame data analysis using LightField automation with Python. As a prerequisite for this seminar, it's best if you review the first two seminars, parts 1 and 2, because we're going to get into some advanced topics, and it would be great if you have a foundation that you can follow up on, because we're going to be getting into some pretty cool stuff with this one. So what we're going to do here, we're going to walk through a Python script that uses event triggers to grab frame data and perform analysis in real time. So again, you want to review the previous seminars just to get an idea of what an event is if you're not aware. So we're going to have a Pixis 400BX system and an isoplane 160 system in combination. We're going to cover the image dataset received event. We're going to use this event to transfer frame data to Python as each frame is acquired. So this is some real-time frame grabbing. And we're going to perform centroid analysis on each frame. So as you can tell, this seminar was inspired by a real application. So we get requests for this type of application where regions of interest or other parameters need to be adjusted based on frame by frame analysis as the data comes in. And you can extend this concept to other applications. For example, in ion trapping, quantum mechanic experiments, you want to trigger some hardware based on the results of the frame. You want to look at a certain region of the frame and immediately decide, do I want to trigger another piece of hardware or not? So this type of concept can extend to many sorts of applications. Um, we're going to discuss this image dataset object and how to exactly to get data out of it. So the image dataset is what the LightField automation interface returns. That's the .NET object. And so now how do we get data out of it, put it in Python so we can process it. And along these lines, we're going to discuss the benefits of using Python to do this, as opposed to some other development environments. So we'll touch on some of the strengths of Python and some of the weaknesses of LabVIEW or MATLAB and things of that nature. And of course, we'll validate the automated experiment by checking the captured data, just to show that what we're getting out of the automation script is actually making sense. Okay, so now let's jump into the script. So I'm going to open my Spider. So let's give this a minute to open, and we're going to go through the script that I prepared and find out exactly how we can do this real-time acquisition. So let's just give this a minute to load. It's coming up now. Okay, so here are my scripts, and this is the script that I prepared for this seminar. So this is TPI PyDemo 2. So let's just go through it. So here are the declarations. Those are all declarations, and you could already see we're starting to import some math libraries in here to do some analysis. So this is one of the many advantages of using Python, and we'll touch on this a little bit later. But so these are all the function definitions, and we go down here. Here we start our, if you will, the main part of the script. So once again, we declare the automation object. This will pop in an add-in process. We get the experiment object. We declare an auto reset event. Again, from seminar number 2, you'll know what this is. We load the experiment. We hook the listener. We initialize the file name parameters. And here's something new. So we're now using a library called PySerial. So I'm going to scroll up. So import serial, and this might be something you have to install with your distribution. You can just do it using the pip install, very easy. But the PySerial will give you a serial command interface to work with. So we're going to open up the spectrometer with the serial command. So this is another way to use the spectrometer. So if you recall from seminar number 2, we used the LightField commands to control the spectrometer. And here we're using another method, and you'll see in a minute why I'm doing it this way. If you recall, the LightField automation commands for the spectrometer were synchronous, which means the thread would lock as soon as the command was issued and wouldn't let anything else happen until the command finishes. So if I was moving a grating, nothing else would happen or be allowed to happen until that grating got to its final position. And since I'm going to be doing some real-time captures and be using some motion to do it, um, I didn't want that here. So I'm going to control it through the serial port, and you'll see how we combine this with the asynchronous acquire and uh, get some moving data, if you will. Um, so our spectrometers, the Teledyne Princeton instrument spectrometers, can be controlled using serial commands. So here I'm on COM port 5. This is the baud rate, it's a parity, all these settings. This will be the same for any of our spectrometers. And you could look at the Pi serial documentation if you want more details on how to use this. It's a neat little library. It's pretty simple to use. So I wrote this function here called clear seer, which is just, let's go up here. We'll just go through our function. It just resets the output and input buffers. So nothing too special. We just clear everything out, flush it, if you will. So we clear that. So here's what we're going to do with the spectrometer. We're going to go, this is a grading move command for the spectrometer. We're going to do a zero go to. Um, we're going to encode it so that the serial terminal knows how to process this string. Because if you just put it as a regular string, it won't know what to do. We got to put it in a we got to put it in a format that it recognizes. And this is the hex for the end line or the carriage return. So we're gonna end the line. We're gonna wait for serial. So here's the function I wrote: wait for serial. So we're going to input an object, and the object that's input is going to be just this serial object that's created from this Pi serial declaration. So basically what this does is it just keeps polling until we see an OK in the string. So what this OK means is when the command entered into the serial port for a spectrometer finishes loading or finishes running, I'm sorry, then it's gonna print out an OK, and that's when you know that the command stopped. So we're gonna kind of initialize this experiment here by going to 0. So we're going to go to the 0 nanometer position. We're going to wait for it to finish. So this would be like the synchronous command. So if you were doing this as we were doing in seminar number 2, you would just enter the LightField automation command, and you wouldn't need to wait for anything because that's a synchronous command. The serial command is asynchronous, so we're going to wait. We have to put in a wait, just like we did with the auto reset event. This is our version of the auto reset event, if you will. We're just going to poll. So we're going to write another command. We're going to select grading, the first grading, so grading number 1. And this is not 0 index. So unlike in the LightField automation where we chose grading number 2 with the 1 index, with saying putting a 1 as the index, this 1 actually means it's the first grading, not the second. So just a little syntax difference there. We're going to once again wait so the grading can get there. Now we're going to start the experiment with the grading at 522 nanometers. And once again, we're going to wait, make sure it gets there, and then stop. So now we're going to set the camera parameters. We're going to set the exposure time to 100. We're going to acquire 20 frames. And you'll see how this comes into play in a minute. We're going to get the width and height. So I have a Pixis 400 BX here, and with an isoplane 160, and it's going to have a 1340 column by 400 rows. So these are going to be width and height, but we're going to get these right from the experiment values. Then we're going to set a base file name, as you recall from seminar number 2. This is just to name the files so that we're aware of what happened. And now here comes the meat of this demo, the acquire, move, and lock. So let's go to the acquire, move, and lock. So now you see in this, when we call this function, we're going to hook this listener in. So again, seminar number 2 covered event listener. So if you need to freshen up on that, just go back to that seminar. We're gonna hook the image data set received. So if you recall in seminar number 2, we used a slightly different event which returned when the acquisition completed. So if we used that one this time around, it would it would return when 20 frames were required. It would trigger the listener. Here, we're going to use this event, the image data set receive, which is going to trigger the listener after every frame that comes in. And let's just go to this automation document, and let's pull up the events one more time, supported events. This is the file manager, sorry. This is the experiment. Where are the experiment events? Supported properties, supported events. Here are the iExperiment supported events. You see image data set received. So now this event is called whenever image data frames are received. For example, in preview mode, each frame will signal an event that data was received. So this is what we want to be using for our live frame captures. So let's minimize out of this. So I'm going to hook a listener. I'm going to print, let the console show that we're ready to acquire. Now we're going to name the files, and we're going to get the exposure time from the camera settings. Again, same thing as in seminar number 2. Again, this is just setting the file parameters. Here we're going to issue the acquire command. And again, this is asynchronous. And as you can see, unlike in seminar 2 where we put the where we waited to set the auto reset event, we're not gonna do that immediately. We're gonna add some other lines after the acquire, and then we're gonna lock the thread. So we're not locking the thread here because now we're gonna move the spectrometer. So if we starting at 522, that's what we initialized it to. Now it's gonna go to 546. So now we're gonna wait for the serial to finish. Then we're going to sleep there for 2 seconds. Then we're going to tell the spectrometer to go to 570. Then we're going to wait again for the spectrometer to finish moving. And then finally, we're going to lock the thread. So we're going to do a little, while this acquisition is happening, we're going to do some motion. And let me now show you exactly what this motion is going to be. So I'm going to open up LightField regularly first, just so um, we're gonna kind of walk through this experiment without the automation, just so we can see what it should do, and then we're gonna go through the callback function for the image data set received event. So here I'm gonna open up LightField. So again, this is not an automation control process. Let's maximize this. So I'm gonna load that experiment. It's loading that experiment here. As you can see, I don't have the ISO plane in the demo experiment. And the reason I'm controlling the ISO plane through serial port, I don't want to control it through LightField because of the asynchronous move as I described. So let's just ignore the experiment for now. Let's load in this ISO 160. So just give it a moment. It'll add the instrument. Okay. Let's put this Pixis back on it. Okay. So we're at the 1800 groove millimeter grading. That's turret 1 grading 1. That's where we want to be. So we're gonna start this guy at 520. So let me put there. I'm just gonna start running it so you can see what's gonna happen. So when the grading position is at 520, the peak of interest is gonna be all the way to the right of the sensor. So somewhere around here. Now when we move it to 546, you can see during the motion of the spectrometer, we're going to get some artifacts while the spectrometer is moving. So our goal is to capture all of this. Now it's going to sleep at 546 for a bit, and then it's going to go to, I actually forgot what it's going to go to. Let me check. It's going to go to 570. So let's put it at 570. Sorry. So you can see it's going to do another motion thing, and now we're going to get a strong peak on the left side with two smaller peak. So this is the 546 strong peak. This is the 576, 579 doublet. So we're gonna get that. So all as this is happening, we're gonna acquire all the frames, and we're gonna calculate the centroids at each of these at each frame, and we can kind of verify that we're getting the correct number, which will prove that we're grabbing the frames live and we're doing a calculation on it in real time and we're getting the accurate results. So that's what this script is going to do. So let's get out of LightField. I'm going to open up my Spider again. And let's just walk through this image data received event. The callback, I'm sorry, the experiment data ready. So this experiment data ready. So if the experiment is ready to run, I set a global variable here. I think I initialize it here. I initialize it to 0 here. So I set a global variable here. I have this frames object which equals the event arg. So event args is the event argument from this image dataset received event, and the event args is an image dataset object. So let's get into this image dataset object. So you see here the event args, I get the image dataset object, and I'm taking the frames property from it. So let's get into this image dataset object. So I'm going to search for this image dataset. So this is just code examples. Let me scroll back up and then let's find it again. So I want like the definition of this. Here we go. So here is the image dataset object. So here are the supported methods. So you can see you can get column, frame, pixel, row, and each of these methods will return an image data object. And here are the properties. So frames. So this property frames, it just tells me how many frames are held by the image data set. And the reason you want to check this is in case there was some lag in the CPU processing and your callback returned multiple frames. So let's go to this image data object really quickly. So let's go to iMageData. See if we can find the let's go to iMageData. So now the image data, the get data is going to return a .NET array object, which you'll have to kind of transform into a Python array with the correct data type, and we'll show this in a little bit. So this is what, once you get the image data object from the image data set, you're going to want to convert it with the get data. So let's go here and let's show exactly what we'll do. So we're gonna increment this global variable by the number of frames we get, so we keep like a running counter of what frame we're on. I call this buffer object, which is this event args image data set. We're gonna get the frame. We're gonna get the most recent frame in the event and in ROI number 1 because we're not changing any ROIs here. Image data. I call this object. We're gonna get data. So this is the get data that returns the iMageData object. And now we're going to manipulate this object with this function that I wrote. And I'm going to input this buffer in here, which will grab the frame and as well as the image data object. So let me go to this manipulate image data. So it's a very simple function. I convert the buffer with this function, and I get the format out of this buffer object. So this get frame object has a property called format, and I convert the buffer with it. So I need to know the image format to know whether it's a monochrome unsigned 16, monochrome unsigned 32, or a floating 32. So I can assign the correct data type to it to kind of cast it into the .NET array. So I use the ctypes library. So this is the import ctype somewhere here. Here, there's the import ctypes. So I use the ctype library to convert it to a C data type, and then I put it into a NumPy array. So the NumPy from buffer method, and we're just going to get this buffer and we're going to put it into this result array, and we're going to return this result array. We're going to return a copy of it, if you will, and we're going to use this GC handle in the Windows system actually. So this is a .NET class, and you can get more information on the .NET the Windows .NET documentation. And that's just going to be to handle in memory and make sure it's free. So this is what we're doing in this. So we're going to get, so we've transformed this undefined array image data object into a NumPy array that Python can use. And now we're going to go ahead and do some calculations with it. So this moment is actually from, where is the import? This moment is from this skimage library, and it's going to calculate the moments of the 2D image. And then from those moments, we're going to calculate the centroid, which is basically this algebra right here. And then we're going to print out the centroid in each direction, the vertical direction, and the horizontal direction. So you'll get to see in real time how this happens. So now that we've kind of walked through the script, let's run this. So let's get to it. So I'm going to press F5, run this. So it's going to open up that add-in process. And you're going to want to pay attention to this console here, as it's going to update every frame. So LightField is loading. And as it loads, I'm going to try to position the window so that you can kind of see the data and also see this console. Again, pay attention to this bottom right-hand side. This is where we're going to print out everything that's going on. So I'm going to reshape the window so that we have a view here. So the application is loading the experiment. It's gonna do those. It's gonna initialize the grading to the position we want to start it at. So it's loading the experiment. Okay, I'm hearing the gradings move, so it's the serial command is doing its thing. And once I hear the shutter click, that's when I know the acquisitions are happening. So shutter's clicking, acquisitions are happening, and you see here we have the motion and we have the live data grab. So now let's go into the image that we just took. So we acquired these 20 frames, and as these frames were acquiring, you could see how the lines updated live. So let's go back in here. I'm going to hit F12 in LightField. We're going to open up this file. So I'm going to let me see if I can position this in a way where you can see the whole frame. Yeah. Okay, okay. So this is frame one. So now as you can see, the centroids for, I'm going to move it. So this console, so you can see centroids for frame one. So now you know what that says. So 202.53, 1205.23. So this part is the vertical direction, and this part is the horizontal direction. And as you can see, throughout all the frames, the vertical centroid doesn't change, as it shouldn't, because we're getting a whole line of illumination. So the dispersion from the grading in the vertical direction is covering the entire image sensor in this case, all the rows. So the centroid is gonna be somewhere around the middle. Again, we have 400 rows, so you would expect the centroid to be around 200 something. So it's really not shifting. So we go through this. See, the vertical positions are we're filling up the entire sensor. So now the centroids here, this is going to be in pixel because we don't have a wavelength calibration when we're controlling it through a serial port. So we're not controlling the spectrometer through LightField, so we're not going to have that aspect. But so 1205 pixels. So as you can see, I'm going to move this right here. So so pixel number 1205. I'm going to move this is right here. So the centroid is calculated to be somewhere around here. The vertical direction is going to be about 202. So this is where it's calculating your centroid, and that's accurate. I mean, this is your main peak. You got a little slight shade of gray here that's kind of pulling this guy back, but for the most part, this is your if you're taking this whole image into consideration, that's where your centroid is going to be. If you're taking a local region, then yeah, then your centroid will be more around here. But again, we're taking the whole image. So let's see. Let's move along. So frame number two, we're getting this motion. So now you can see the centroid move to the left. So now we're at 1061. So where is this? 1061 would be right here, and you could kind of remove this just a hair, and you could see this right There we go, 1061. So you can see our calculations are still good. And again, remember that it's grabbing this live. So as you're acquiring, it's grabbing this data. So you can do, based on this centroid calculation, if you wanted to trigger something or you wanted to shift another piece of hardware, you would be able to do that. So now it's moving over to the left. Now the centroid is around 748. And you can see I'm just getting an estimate based on where I see the white blob, and that's around where the centroid is happening to be. And move it again, 652. There we go. Here's 652 right here, and you see this guy's kind of stirring a little bit. 652. Now the I'm sorry, the grading is settled. You see how the centroid. So now we're gonna keep going. Now it's in motion again. So it starts motion in frame 9, and bingo, there we go. Now the centroid's changing again in frame 9. So now we go to 632. This is the centroid right here, 632. Keep going. Now go to 477 in frame 10. So where is 477? 477 is right. Keep moving. Right there. And you can see we got this blob right here, um, which is kind of dominating. But now we got this little spike right here, and we got this blob right here, which is less dominant. So that's why the centroid is on this half. And as we keep moving it, as the peaks become more defined, as we're getting closer to the position we want, now the centroid is moving. Now it's at 226. So here now 226. Let's just keep going, and the centroid kind of settles in around 219, 220. So we have, where's 219? There we go. And again, we got this bright peak here, but now these two little guys are kind of dragging the centroid just a hair to the right. So now we've settled in on this. You see we end frame 20 with the spectrometer in its final position, and there's your centroid. So you can see that we validated our live, I'm sorry, why did that just disappear? Our live calculations with this, um, with the acquired file that we saved out. And you can see the calculations were accurate, and we were able to do the real-time data grab. So why do we want to do this in Python? Python has a few advantages, and I would actually say many. I personally love using Python. It's my preferred development environment of choice. Now, the three options we have, actually four if you include C Sharp, which is the sort of native .NET application. But if you're going sort of outside IDEs, we got Python, MATLAB, LabVIEW. So this is again my personal opinion. I hate LabVIEW. I don't like programming in it, and it's just, it's not really. A lot of labs use it, but it's for data science and for hardcore analysis. It's just really, I don't, I'm not a big fan. And when it comes to debugging code, I'm not a big fan either. Again, it's just my personal opinion. MATLAB, I love. Graduate school, I went through using MATLAB, but the drawback of MATLAB is the .NET support for the events. For whatever reason, we found that it can't handle this image data set received event. The listener will hook fine, but the once the callback happens, the event argument actually gets disposed before anything can be read. So that probably indicates that there's some sort of lag, or the MATLAB interface is just too slow to grab the event, which is unfortunate because if you're trying to do real-time processing, you need to grab that event. So MATLAB works great for all, like 99% of LightField automation, and totally encourage you to use it. I love MATLAB. It has lots of math functions, analysis functions, statistics functions. It's wonderful, but this is just the limitation for the live data grabbing. It just, I found that, I can't, if I do this exact thing that I did in Python with MATLAB, it wouldn't work. This object would just be disposed, and that's sort of unfortunate. Which brings me to Python, which is, as I mentioned, my favorite way to do this type of development. And Python's amazing. It's open source. It has all sorts of libraries that are in peer-reviewed art used for peer-reviewed articles, and they're verified. The SK image, the NumPy, sklearn, um, uh, the and all of these, you want to calculate moments, you want to calculate centroids, it's just two lines, as you can see. And these are all, verified, open source. You can see exactly how the calculations are done to verify their accuracy. So Python is what you want to be using for this. And you can see how easily you can just import a few Python libraries, and you can do things like serial command. You obviously have the .NET control with LightField, and now you have the math power. You got the NumPy to kind of transform the data into Python array, and you could see I did all of this as a 2D array, and it was fast enough. I didn't even have to manipulate indices to kind of read it as 1D for speed, and it's just everything just works out great. Um, so yeah, I love using Python. Again, this last bit of the seminar where I go through my opinions on this, on using these development environments. That's my opinion, but again, there's a reason why I'm doing these seminars in Python, and cool things like this. It's just Python makes it so easy. So thanks for watching this seminar. I hope you got some educational information out of it. Once again, we walked through a script to show how to grab data live out of LightField automation, and we also showed how to control a spectrometer using the serial command and kind of use the asynchronous nature of the acquire function to get some moving data, if you will, out of the spectrometer. And we went through the image dataset object and showed how you can get a Python array out of this sort of amorphous array that the image data is returned as by LightField. And then we went through some validation to show that the centroid calculations were accurate. And I just shared my opinions on why I love using Python for this type of stuff. Python just makes everything so easy. So I hope you enjoyed. Please feel free to send us your questions, comments. We can be reached at pi.techsupport@teledyne.com. Once again, I'm Sabir Leacat, an engineer at Teledyne Princeton Instruments, and thanks for watching.